Hello YouTube. In this video I'm going to look at an argument for scientific realism developed by Seng-May Park. I'm not sure if I'm pronouncing his name correctly, but anyway, developed by that guy in various articles and in his book Embracing Scientific Realism. And this is what he calls the optimistic induction. So if you're not familiar with the scientific realism, anti-realism debate, I have a whole series on it, and I would recommend watching at least the introductory video before watching this video, because I'm just gonna assume a bit of background knowledge here. Okay, so what's interesting about Park's argument is that he tries to turn some of the standard anti-realist tools against the anti-realist. In particular, a classic argument for anti-realism is the pessimistic induction. In its simplest form, the pessimistic induction goes like this. Most past successful theories were rejected in favour of alternative theories, so probably most of our current theories will be rejected in favour of alternative theories. The anti-realist looks at the history of science and she finds what Larry Loudon once called a graveyard of failed theories. The history of science reveals a host of theories that were successful in their day, but that turned out to be false. So one important point about the pessimistic induction is that we have to go quite far back to find this graveyard of theories. In many scientific domains, you have to go back, 60, 70 years. In some cases, you've got to go back well over a century. If you take our fundamental, well-established theories today, general relativity, quantum mechanics, the modern evolutionary synthesis, the Big Bang model, the germ theory of disease, the citric acid cycle, the periodic table, plate tectonics, well, there's this body of scientific theory here that, in its fundamental commitments, has been stable for at least half a century, and in some cases a lot longer than half a century. So yeah, if you sort of go back to the 1700s, then okay, well, back then they had, Newtonian mechanics, they had corpuscularian theory of light, they had, the caloric theory of heat, the phlogiston theory of chemistry, but, looking at just the last sort of 50 years, what we find is stability. This challenges the pessimistic induction, but more than that, it suggests an alternative positive argument for realism, and this is Park's optimistic induction. So the basic idea is this. When we examine the recent history of science, we find that our most well-developed, well-confirmed theories have not been falsified, despite decades of severe tests. Now, of course, every theory has faced some challenges, and there will have been minor changes, but the basic claims have been confirmed over and over and over again. And they've been stable, they have been retained. So we can make an optimistic induction. Since well-established scientific theories have survived these tests in the past, they will continue to survive these tests in the future. Right? Since they have been accepted in the past, they will continue to be accepted in the future. Consider the sort of realists of the early 1900s, right? They believed that their best theories were true on the grounds that those theories were empirically successful. From our vantage point now, we can see that they have pretty much been vindicated. The theories that they thought were true, we still take to be true. So, as far as the optimistic realists of today are concerned, the optimistic realists of the early 20th century were largely correct. And then we can inductively infer that we're probably in the same position. When our descendants look back on us, they will judge that we were correct to believe our best theories. And so this kind of reverses the standard pessimistic induction. So we have these two inductions. We have one pessimistic, one optimistic. Which is the more convincing? Well, there's a major problem with the anti-realists' pessimistic induction, which is when we make an inductive inference from historical cases to the present case, we need to make sure that the cases are relevantly similar. So we need to make sure whenever we make an induction, we need to make sure we're making an induction from a representative sample. So let's say that a new variant of coronavirus emerges, and I see that it has a 50% mortality rate in observed cases, and then I infer, oh my goodness, right? I better hope I don't get this, otherwise there's a 50% chance that I die. But now suppose I discover that this new variant has so far only infected people in a retirement home that was specifically for people who were, exposed to radiation or something. So, most of them have cancer. Well, okay. Obviously, if I were to contract this new variant, I can't conclude that my risk of death is 50%. I'm younger, I'm in otherwise good health. That makes a difference. Now, the trouble with the pessimistic induction is kind of the same thing. It's the pessimist points to theories in the history of science, theories from 100, 200 years ago, but science has changed significantly in that time. Today we have all these new instruments that can penetrate more deeply into nature. We have particle accelerators, gamma ray telescopes, magnetic resonance imaging, all this stuff. We have a whole set of sophisticated techniques for experimental design. I mean, for us, when we talk about things like double blinding or randomized control trials, I mean, that just seems obvious, but actually those things only became widespread in the 20th century, so we have all these new techniques. We have a much better understanding of the circumstances under which particular experimental designs are appropriate. We have all these improved methods of data analysis, statistical tools like analysis of variance, a much more sophisticated understanding of probability and probabilistic fallacies, and like all of this stuff, there was a massive explosion of progress over the 20th century in so many fields of science. But what this means is we can't infer from the failure of past theories to the failure of present theories. There is no reason to expect that present theories will suffer the same fate as past theories because modern science is so different. And I mean, prima facie, it seems to be much more reliable than past science, right? Like that seems to be what we have achieved with all of these new instruments and new techniques. The pessimistic induction only works if you assume that modern science is, relevantly similar to past science, but that just seems to be false. So with the pessimistic induction, we're appealing to theories in the distant past. The optimistic induction, by contrast, makes an inductive inference from the recent past. Right? We're looking at the state of science over the last 50 or 60 years. That's important because if we look at the recent past, the methods and tools used by scientists, the institutional structures of science, these are pretty similar to science as it is today. So this is the difference. The pessimistic induction looks at the dynamics of science in the distant past and draws a conclusion about contemporary scientific theories. But scientists worked in completely different ways in the distant past, and that undermines the inductive inference. The optimistic induction, by contrast, looks at the dynamics of science in the recent past, draws a conclusion about contemporary scientific theories. That's more appropriate because scientists in the 60s and 70s, they have a lot of relevant similarities to contemporary scientists. The optimistic induction is a stronger inference. It's more analogous to saying, this new variant of COVID has infected working people under the age of 40 in a particular town and it has a 5% mortality rate. Well, from that data, right, I mean, even if it's only from one town, if it's people under 40, I might say, okay, it's more reasonable for me to draw a conclusion about my risk. I mean, it's certainly more reasonable to draw a conclusion from that data than it is from the, 90-year-olds with cancer in a retirement home. So that's the basic optimistic induction. And Park presents this as a new argument for realism. The standard argument for realism, as you will know if you've seen some of the previous videos, is the no miracles argument. This is the claim that the success of science would be a miracle if our best theories were not at least approximately true. With the no miracle argument, we have an inference to the best explanation. So there's this sort of surprising phenomenon, right? The remarkable predictive, explanatory and technological successes of modern science. And our question is, what explains this, right? What explains the success of science? The realist who makes the no miracles argument says that the best explanation for this success is that our theories are true. Well, yeah, that's a straightforward explanation, but there are a lot of objections to this argument, not least the fact that many anti-realists just don't accept inference to the best explanation. So if you're not on board with inference to the best explanation in the first place, then an inference to the best explanation to realism isn't going to move you. But with the optimistic induction, the realist has a totally new tool. This is not an explanatory argument. It's a sort of simple enumerative induction. So that's that's the basic argument. But Park then presents another couple of arguments that are designed to strengthen this. And these arguments, again, quite cleverly appeal to ideas that have been developed by anti-realists originally. So again, Park is sort of turning the anti-realist weapon against them. So a recent, quite influential argument for scientific anti-realism is the problem of unconceived alternatives. This was originally developed by Kyle Stanford, and I've got a couple of videos on this. So, like the pessimistic induction, this appeals to the history of science. Stanford says, when we look at the history of science, we see that scientists very often simply failed to conceive of alternative theories to the theories that they accepted. So, there were alternatives that were just as good, in fact sometimes better, than the theories that they accepted, but they just failed to conceive of them. So, they weren't even able to evaluate, they sort of didn't even realise the limits of their own ignorance. So consider, for instance, that all of the evidence for Newtonian mechanics supports general relativity. But for hundreds of years, general relativity was never even considered as a competitor to Newtonian mechanics, because no one had even conceived of it. So there were scientists who, were looking at this incredible success that Newtonian mechanics was having. Like, it was if you go back to the 1800s, it was the most powerful theory that had been developed, right? Like, in terms of its empirical successors and the sort of control it gave us of various phenomena. Incredibly successful theory. They were looking at that and they were saying, well, this must be true, right? That's the only way we can explain this incredible success. It must be true. But it turns out there was this alternative theory that would have actually done just as good a job. In fact, a better job. But no one had conceived of it. And that's what we find, right, over and over again, is we're just really bad at actually coming up with alternatives. So Stanford says we should similarly expect that there are unconceived alternatives to the theories that we accept today. That is the the unconceived alternatives argument. Right, so Park is going to turn this argument on its head. What we actually find, Park says, much more commonly in the history of science, at least the recent history of science, is not that there were these unconceived alternative theories, but that there were unconceived neighbouring theories. So what is a neighbouring theory? Well, theories that are confirmed independently can sometimes be conjoined so as to predict or explain new phenomena, right? So I might have like two theories from different domains, and then I find that when I put them together, I'm able to make a whole load of new predictions that also get confirmed. These are neighbouring theories. And when we have neighbouring theories, this lends greater credence to both theories because they're like mutually supportive. One of the examples that Park gives is electromagnetism and evolutionary theory. These are two theories from different fields of science developed in response to completely different problems. But there are these interesting connections between them. So consider the question, why do people have different skin pigmentations, and what explains the geographic distribution, the patterns in the distribution of skin colour that we see? Well, the explanation is something like this. Evolutionary theory tells us that our ancestors evolved in Africa. Ultraviolet light destroys folate in the blood vessels of the skin, and lack of folate can lead to a variety of negative health effects. It's especially important during infancy and pregnancy because it plays a role in cell growth. Now, dark pigmentation protects the folate. So there was selection for dark skin. When the hominids began to migrate from Africa into the colder, cloudier climates, well, there's no longer much risk that sun exposure is going to destroy the folate. But there was, however, the problem that there was not enough exposure to ultraviolet rays to generate vitamin D. Again, vitamin D deficiency has negative health outcomes. So now there's, in the colder climates, there's selection for lighter skin pigmentation, which more easily... with the lighter skin, you're going to more rapidly produce vitamin D in response to ultraviolet light. Okay, so what we have here is an explanation that's appealing to both evolutionary theory and electromagnetic theory to provide an explanation for the pattern of skin colour that we observe in the human population. Here's a second example. Evolutionary theory and plate tectonics. So this is an example of a prediction. So evolutionary theory plus DNA evidence indicates that marsupials originated in South America hundreds of millions of years ago. Plate tectonic theory tells us that South America, Antarctica and Australia were once connected and drifted apart over millions of years. On that basis, we can predict that marsupials would have migrated from South America to Australia via Antarctica. So, if this is right, there should be fossils of marsupials in Antarctica. Neither evolutionary theory nor plate tectonics alone predicts marsupials in Antarctica. We can make that prediction when the theories are conjoined. And as it turns out, that prediction was confirmed. There are indeed marsupial fossils in Antarctica, which can be dated to the time that the migration of the marsupials was predicted. So evolutionary theory and plate tectonic theory cohere. And I mean, there's numerous examples like this. Now, the key thing to notice about this is that these positive connections between the theories were unexpected. It might not have happened this way. There was no guarantee that these theories would support each other. Plate tectonic theory was proposed long after evolutionary theory, and it could have caused problems for it. I mean, if on the basis of plate tectonic theory we concluded that the Earth would have been completely submerged underwater until the last 50 million years, which, we might have done, right? We might have discovered something like that. That would have been difficult to square with the assumption that there were land animals during that time, and who knows, maybe it would have ushered in a revolution in biology, but didn't happen, right? Instead, we find out that they cohere. And these examples could be multiplied indefinitely. One of the most notable features of modern science is that it's systematic. It is incredibly interconnected and interdisciplinary. It's not just that there are a bunch of well-confirmed theories. Each theory has indefinite connections to other theories. Completely different domains of science intersect in all sorts of ways. And so, the kind of evidence that originally supported, say, electromagnetism, well, that's completely different to what originally supported evolutionary theory, which in turn was completely different to what originally supported plate tectonics. And yet we can find all of these cases where, it's not just that these theories are consistent with each other, they are actively conjoined. It's arguable actually that evolutionary theory, at least the modern evolutionary synthesis, so, the combination of Darwinism and Mendelian genetics that occurred in the 1930s and 40s, arguably that's just never clashed with a well-confirmed neighbouring theory. It's just never happened. There have been challenges to specific claims, but the sort of basic foundational kind of propositions, they've never clashed with anything. There's been no major alternative. So with this in mind, we can make an optimistic argument from unconceived neighbouring theories. In the past, evolutionary theory has been supported by numerous well-confirmed neighbouring theories that were, at that time, unconceived. So, by induction, evolutionary theory will continue to be supported by neighbouring theories in the future, neighbouring theories that are presently unconceived. Evolutionary theory basically has been supported by neighbouring theories in the past. It will continue to be supported by neighbouring theories in the future. And, obviously we can make the same kind of argument for a whole bunch of well-established theories. Anti-realists like Stanford are quite right that the history of science suggests that there are many unconceived theories that will be empirically successful. But it also suggests that these theories will not be rivals to presently accepted theories. Rather, they will provide further confirmation to presently accepted theories. The modern evolutionary synthesis will continue to be bolstered by new theories that are developed in the future. Is that convincing? Well, so one worry we might have about this appeal to neighbouring theories is, so when theories are conjoined to predict or explain new phenomena, it often requires quite a lot of work to kind of figure out how the theories fit together. So scientists will construct models that are explicitly designed to take the well-confirmed assumptions of each theory as a constraint, right? It's not that we have these two independently confirmed theories and then the conjoining models just drop out. We have to put some effort into making these models. And if we come up with a model, which violates the established assumptions of one of these theories, so, if I was to develop a model that just violates the established assumptions of electromagnetism or evolutionary theory or plate tectonics, well, it would just be rejected, right? We probably wouldn't even consider it. In the example of explaining patterns of skin colour, note that the key feature here is the connection between sunlight, health effects, and skin colour. I could propose a model that appeals to, the corpuscularian theory of light, which would describe corpuscles of sunlight interacting with the skin, and that could similarly explain, patterns in skin colour. But, what would be the point of that? No one's going to develop that model, because obviously when we construct these models, we appeal to accepted theories. So, an anti-realist might kind of look at this and say, well, Well, yeah, I mean, of course we should expect to find lots of neighbouring theories. The reason for that is that scientists are intentionally constructing models that build connections between theories. In the same way, of course we should expect that future theories will be empirically adequate because we're intentionally constructing, theories and models that are supposed to be accurate to the observations. Like, that's a constraint. If I have a model, if I come up with a model that doesn't make the right predictions, I'm going to reject it. Obviously, right, when we look at future science, assuming it works the same way as present science, we should expect to find like models and theories that make lots of correct predictions that are empirically, or at least approximately empirically adequate. It's just the same. It's the same thing with neighbouring theories, right? Like, we're intentionally constructing models that find the sort of forge connections between theories. So maybe an anti-realist can sort of, instead of saying, well, the reason for this is truth, they can say the reason for this is because this is what we're intentionally constructing. Maybe. Okay, but there are not just unconceived neighbouring theories. There are unconceived alternatives to all kinds of things in science. Again, anti-realists like Kyle Stanford, for instance, will use unconceived alternatives to other kinds of things to challenge our belief in current theories. Theories of the past were challenged by things that in the past, so previously, unconceived instruments, unconceived observations, unconceived methods, unconceived models, in general, like unconceived evidence, right? So with new developments, unforeseen challenges to our accepted theories may arise. Like for instance, right, Ptolemy's geocentric theory of the solar system was disconfirmed partly due to the invention of the telescope and the observations of the phases of Venus through the telescope. That occurred centuries after Ptolemy's life, and that's something which, he might not have even been able to conceive of, right? The idea of a telescope. That just didn't exist when he was writing, and for centuries afterwards. So, just as past theories were challenged by unconceived alternative theories, right? They're also challenged by unconceived alternative evidence. Sorry, by unconceived evidence, not unconceived alternative evidence, just unconceived evidence. And an anti-realist looking at that might say, well, we should expect that present theories await the same fate, right? There's unconceived sources of evidence, right, that will probably challenge our presently accepted theories. Again, Park turns this around on the anti-realist, right? So he would say, well, of course we have to accept it's possible that some unforeseen challenge will arise, but actually when we look at our most well-confirmed theories and we look at the history of science there, it's not reasonable to expect this. The history of science suggests the exact opposite, that unconceived evidence will only tend to provide stronger and stronger confirmation to these theories. So new developments, right, new source of evidence, when we look at the history of science, we see that what happens is new sources of evidence just seem to provide more and more confirmation to the theories that we accept. So if we look at general relativity, for instance, okay, that was proposed in 1915, and since that time it has been tested over and over and over again against a variety of different sources of evidence. Some of these tests were possible in the early 1900s, Eddington's eclipse photographs and so on, but since then all these new methods and new tools have been developed that have been used to test the theory. So, brief list. In 1971, the time dilation prediction, the degree of time dilation predicted by general relativity was confirmed by flying jets around the world with atomic clocks on board and then comparing the time on the jet clocks with the clocks that remained on the ground. Similarly, the GPS system was obviously designed with relativity in mind, and its continued functioning every day confirms the theory's prediction concerning time dilation, that time slows as an object moves faster. Particle accelerators confirm the prediction that the mass of an object increases as it moves faster. The decay of the orbital period of pulsars matches general relativity's prediction of energy loss from gravitational radiation. And I mean, moreover, we've now actually detected gravitational waves. First detection occurred in 2015, a century after general relativity was proposed. In 2019, the first image of a black hole, the size of the shadow matched the prediction of general relativity. This is a very brief list, right? There's a whole bunch of other tests. Now, these methods of testing did not exist when the theory was first proposed, and I mean, like, some of them weren't like even like known about or conceived of. I mean, pulsars, for instance, were not known when Einstein first proposed his theory. Nobody was talking about them. That was like a surprise discovery. So the theory has been confirmed over and over by these previously unconceived instruments and methods. By induction, we should expect that, you know, currently unconceived instruments and methods will be conceived in the future that will also confirm the theory. So, as Park says, since relativity has been repeatedly reinforced by new methods, it will continue to be reinforced by new methods indefinitely into the future. And all of this supports an optimistic induction. Right? Our well-established current theories will probably be retained over the future course of science. All right, here is a concern about this argument. So Park is claiming that we can expect our well-confirmed theories to continue to receive confirmation indefinitely from currently unconceived sources. The problem is that isn't the same also true for theories that have actually been falsified? Take Newtonian mechanics. Well, Newtonian mechanics will also receive endless confirmations from currently unconceived sources, because Newtonian mechanics does correctly describe objects within a particular range of masses and velocities. So, like, many of its predictions will continue to be confirmed. Now, obviously, we will not treat these as like confirmations of the theory, because we now know that the theory is false. It's been replaced by general relativity. But we only know that because we've penetrated into those parts of nature where its predictions fail. Everywhere else, it continues to have success after success. You know, you can simply say, well, hey, look, you know, when we sent the probe to Pluto, right, like, we used Newtonian mechanics to do that. So, you know, that's another like success for Newtonian mechanics. So it's important to distinguish between two claims, right? So first of all, there's the claim that some of the theory's predictions will be confirmed by unconceived sources indefinitely. The second claim is that none of the theory's predictions will ever be disconfirmed. Now, obviously, that second claim is a lot stronger. And we might say that the historical evidence only allows us to infer the first claim. I mean, after all, all it takes is one wrong prediction to falsify the theory. Well, I mean, it might be a bit more complicated than that in practice, actually. You know, we're not going to throw out a whole paradigm on the basis of one failed prediction. We'd look at altering auxiliary hypotheses, and I mean, I guess in any case, realists acknowledge that our best theories are only approximately true. So yeah, they might be mistaken in some ways. But I mean, look, the point remains, right? Like, it's we might say, well, look, it's not enough, right, for the optimistic induction to say that a theory is going to continue to rack up confirmations. What you need to show is that it's going to avoid disconfirmation. And I don't know, the historical evidence is, we might say, it's a bit less clear about this, right? So it's fine to say, yeah, we're going to find sources of evidence that continue to confirm it, but you know, can we sort of take that further leap and say it will always avoid disconfirmation? That's not so obvious. Okay then, so we've seen the general optimistic induction argument. I've noted a couple of objections to some of the specific ways that Park tries to strengthen that argument. What I want to do before ending is note just a few general objections to the optimistic induction. So, one objection is that there are some cases where our best theories are just straightforwardly incompatible with each other, so that we can expect these theories to be displaced in the future. The classic case here is the problem of reconciling general relativity and quantum mechanics. Each of these theories is among the most empirically successful theories ever proposed. I mean, I say among, right? They just are, right? Like, they are the most, empirically successful theories ever proposed, I think. And yet they appear to be incompatible. And this undermines the inductive inference that they will be retained. In fact, it doesn't just undermine it. Like, we know that they can't both be retained. It doesn't matter how strong the inductive argument is, they're inconsistent, so at least one must go. What might Park say about this? Well, first, so Park does note this problem, and he has... So one thing he says is, well, look, the optimistic induction gives us good reason to think that general relativity and quantum mechanics will be revealed to be approximately true by the successor theory. right? So these theories will probably be reconciled in a way that, yeah, I mean, there may be some changes, right, some alterations, but we're going to preserve their claims about the fundamental structure and nature of the universe. So as a general point, I think this is fair enough, right? Like, realists only need approximate truth, and two theories can be approximately true and yet still inconsistent. Whether this is plausible in this particular case depends on the details. Now, I should say I'm far from an expert on physics, but my understanding is that one way in which this kind of incompatibility manifests itself is that general relativity is deterministic, and it represents like fields, gravitational fields, as continuous entities, whereas quantum theory is probabilistic and represents fields as discontinuous, composed of discrete quanta. Now, it's hard to see how those claims could turn out to be approximately true. Now, I mean, of course, these like how both of those claims could turn out to be approximately true. Now, of course, these theories do get a lot of things right. They wouldn't be so successful if they didn't. But the question for realism is whether the description that they give of the fundamental nature and structure of reality is correct, right? Like, so, and the problem is that, you know, if you have one theory that's saying, like, okay, these fields are discontinuous, and you have another theory that's saying that these fields are continuous, well, it just seems like prima facie they're representing the world on a fundamental level in very, very different ways. So, you know, that might be a problem here. But a second point about this objection is that, well, you know, it's just one example, right? Like, actually, we don't find many cases like this. We don't find many examples of well-established, well-confirmed theories that clash in this kind of way. In fact, this might be the only one, right? Depending on you know, how exactly what exactly you want to count as a well-established, well-confirmed theory. This might be the only example. So we could just grant that the optimistic induction doesn't apply to general relativity and quantum mechanics. After all, it's an inductive argument, right? We don't need to say that all of our well-confirmed theories will be retained, just that most of them will. So that might be another response. A second objection is that Park is underestimating the impact of gradual changes. Park says that when we look at recent science, we find stability. We find that our basic assumptions about the workings of nature today are the same as they were 50 years ago. Now, yeah, that's fair enough, right? Like, what's true, certainly, is that there have not been any major conceptual revolutions. We haven't seen whole paradigms being thrown out, like in the, you know, Copernican revolution or the chemical revolution. But the thing is, there have been a lot of gradual changes, right? So consider the modern evolutionary synthesis. Since like about 1950, right, we can say, yeah, the fundamental claims, right, they've remained in place, but it has been developed in all sorts of surprising ways by ideas like endosymbiosis, lateral gene transfer, punctuated equilibrium, epigenetic inheritance, niche construction, superorganism theory, evolutionary developmental biology. You know, some biologists today talk of an extended evolutionary synthesis. A few of them even suggest that the modern synthesis has effectively been falsified, right? So, I mean, okay, there hasn't been a revolution, but it looks like there are plenty of things that the modern synthesis, you know, missed, plenty of things that it even got wrong. So there's been these gradual changes, and as any good Darwinian would know, gradual changes accumulate, and if we project gradual changes far enough into the future, well, you're going to end up with big changes. So you're going to end up with something profoundly different from the modern synthesis. And with this point in mind, it's really not clear that Park's induction helps the realist at all, because, look, I mean, in every field of science, right, we have seen gradual changes. And the kind of gradual change that we have seen in recent science will, over time, you know, give it enough time, it's going to do the same job as an outright conceptual revolution, right? So, like, whether we kind of look back into the past and we see conceptual revolutions, or whether we look back and we see, like, gradual changes, either way, we should expect our current theories to be displaced, right? So, like, maybe we end up actually with just another pessimistic induction. A third objection is that there are many reasons why a scientific field may exhibit stability, that like have nothing to do with realism, right? So there are many explanations of stability that don't appeal to truth. Even if the optimistic induction argument works, right, what it tells us is just, the future development of science, right? Like the future of science is going to look quite similar to the present, right? So currently accepted theories are going to be retained. But the realism debate is about whether or not our best theories are true. And the fact that a theory is retained, that doesn't entail that it's true. So like, granting that our best theories will be retained, why might this be? Well, an anti-realist might point out, well, look, as science develops, it becomes increasingly difficult to propose alternative theories. And there are several reasons for this. The first point is just that theories today are much more empirically successful than they were in the past, right? Their predictions are just much, much more precise. What this means is that, first of all, the cost of abandoning a particular theory is much higher. And secondly, it's harder to come up with an alternative theory that exhibits the same degree of empirical success, right? Like even if there are alternative theories that would exhibit the same degree of empirical success, it's just going to be harder to come up with them. As the sort of standards raise, as the predictions get more and more and more precise, it's going to be harder and harder to come up with alternatives that exhibit the same degree of success, even if those alternatives are available, at least in principle. Bear in mind, it takes decades to develop even a single adequate theory. Our best theories today have been built on, centuries of work. So, we might just get to a point where, it's just not possible for us to or it's just exceedingly difficult for anybody to develop an alternative. A second point is that there is the need for increasingly precise evidence. Eventually, we might just reach a point where the potential evidence that would pose a challenge to accepted theories just outstrips our technological capacities. And we may be getting to that point in some cases now, today, right? We may be getting to the point where we're just unable to test theories in ways that might reveal anomalies. I believe I once read that in order to test string theory, it would require particle accelerators the size of galaxies. So, we're not going to have that, right? So, if you get to that point, then you're not going to find the anomalies that would potentially refute the theory, right? So there's going to be no motivation to put in the exceedingly hard amount of work of coming up with an alternative. Third, there is the systematicity of science, as we mentioned earlier. As we develop models that draw on theories in different domains, we are creating tighter and tighter connections between theories. The web of science becomes denser and denser. We're at the point now where overthrowing one theory, it would just require completely upending all of science, so if you were to sort of, even if you were somehow to come up with an alternative to the periodic table or something like that, so some completely different approach to chemistry, well, you couldn't just do that in chemistry. It would have ramifications through all different domains of science. So it really would require a complete revolution in our whole worldview. Fourth, we might look at the institutional structure of science. It might be that as science has become more professionalized, as it has shifted from the work of gentlemen specialists to being done by large research teams in academic institutions, it's just become more conservative. It might be that the social and professional environment of science these days makes it more difficult to explore genuinely novel ideas. So those are just some suggestions. The point is, there are many factors that could result in stability. So even if we make the optimistic induction, we might just attribute the stability to these other factors. Now this point raises a fourth issue, which is, I mentioned that Park presents his argument as an alternative to the standard no miracle argument for realism. Unlike the no miracle argument, the optimistic induction does not appeal to an inference to the best explanation. Instead, it's a straightforward enumerative induction. But actually, I'm not sure that the optimistic induction is an alternative. The problem is that an anti-realist can accept that our current theories will be retained. And in fact, some anti-realists are explicitly committed to this. According to constructive empiricism, to accept a scientific theory is to believe that the theory is empirically adequate, that is, true of the observable phenomena. Now, if a theory is true of the observable phenomena, it's never going to be disconfirmed. right? So presumably it will never be displaced, right? Which means, so a constructive empiricist who accepts scientific theories is going to expect that those theories will just be retained indefinitely. A constructive empiricist, in principle, could use the optimistic induction as an argument for their position, for the claim that the theory is empirically adequate. So if we're going to argue for realism, for the claim that our best theories are approximately true, it looks like we need to do more than just make the optimistic induction. I mean, the optimistic induction might be part of the argument, but it's only going to be part. So what more do we need? Well, presumably, what we're going to have to do is start talking about explanation, right? The question is, what's the best explanation for the continued retention of our best scientific theories? Granting that our best theories will be retained, that they will continue to be unified with other successful theories, that they will continue to deliver confirmed predictions from currently unconceived sources of evidence. Granting all of this stuff, what's the best explanation for that, right? Do we explain this remarkable success by saying that the theories provide true descriptions of reality, or not, right? Well, at that point, we're just talking about the standard no miracles argument, which means that Park has just failed to give a new argument for realism. I mean, he's not done nothing, to be clear, right? It may be that the optimistic induction somehow helps, provide further evidence or provides further support for the standard no miracles argument, maybe. Certainly the optimistic induction kind of challenges some of the standard anti-realist strategies. It's like giving an alternative to the pessimistic induction, to the unconceived alternatives argument. Maybe it does that, but it's not clear that we actually have a new positive argument for realism that is different from the no miracles argument. Right, that's all for today. Thanks for watching.